Hello students, welcome back. I don't think we're going to do a lot of exponential and logarithmic equations in this course, but let's review that a little bit. To a certain degree we may have to use. Alright, review of exponential rules, special exponents, same base, and same power, and then logarithmic rules, cancellation rules, and then the standard rules. These rules correspond to these rules with the same base. Multiplication is becoming addition, division is becoming subtraction, and then power is coming out as multiplication, sort of multiplication too. And then the change of base rule. A to the x power e to the x times log of a, natural log of a. So everything can be written in terms of natural exponential and natural logarithm. And how about this one? Log base a of x is log of x over log of a. Base down here goes downstairs, so it's easier to understand. Proving is a little bit tricky for this one. That one is relatively easier, but let's not worry too much of those. Everybody should remember those rules anyway. And then how about some natural exponential equations? Well, these kind of problems are quadratic. That too is quadratic. These kind of problems are linear. Let's see, let's do one quadratic equation, and then we'll focus a little bit more upon linear types. Okay, how do I solve it? Well, this is quadratic because e to the 2x power is. This is e to the x squared. So you can rewrite the equation like this. Oh, as a matter of fact, I skipped a step. Oh, never mind. Original problem is over there. So let me rewrite like this. Okay, here we go. E to the x, and then e to the x squared like this. So this is quadratic. This thing squared, and then this is first power. So you can factor with respect to e to the x. You can use tic-tac-toe or whatever, you're going to get this. And then setting the first factor equal to 0, you get e to the x is 1/2. And then setting the second factor equal to 0, we get e to the x is 3/2. Now you're looking for x, not just e to the x, so we take the logarithm of both. So take the log of this, then log of exponential cancel each other out, and here I get log. So we get this. And then taking a log of this, log and exponential cancel each other out. Here I have log of 3/2. That. Both are valid solutions. Always check whether those actually make sense by plugging those back into the original equation. I changed my mind. Let's do one more. Another quadratic. You see? Wait a minute, this is typo. 2x power. So that's second power. Sorry about that. This was just pure typo. And then 5 e to the x power. Okay, all right. And then we can factor. You can use tic-tac-toe or whatever. You're going to get like this. And then setting the first factor equal to 0, we get e to the x is 1/2. This one, which I'm highlighting in blue. And setting the second factor equal to 0, I get e to the x is equal to -3, which I'm highlighting in red. Now please note that the red one is impossible. Why? E to the x is always positive. Look at the graph of exponential function. Where is it? Exponential function, the graph of exponential function. Yeah, it's always positive. Also, please remember, exponentials are basically repeated multiplications and divisions. Repeatedly multiplying or dividing a positive number will never give you a negative number. So that's impossible. This is possible. So this is extraneous. Fake solution, throw it away, and take the logarithm. So log of this, and then exponential cancelled out. We get log of 1/2. Now, if you put log of this and get log of -3 and punch the calculator, you're going to get an error message. That's good, because that means this is an extraneous solution. You have to throw it away. So be careful. Sometimes there are extraneous solutions. Exponentials are always positive. Never mind about this one. If you have time to burn, you can try on your own. Let's go with this. Okay, this is a linear equation because I have no other exponential being multiplied. So let's use standard process to solve a linear equation. We have denominator, so let's use bigger font. Step 1, remove the denominator. Step 2, break up parentheses. Step 3, take care of the like terms. Remember that. Number 1, denominator. Number 2, parentheses. Number 3, like terms. If you remember the 3-step process, you'll never miss any linear equation. Sorry about that. Wrong cell. Okay, alright. Multiply the denominator to both the left-hand side and right-hand side. We get that. As a matter of fact, I skipped a step. Okay. Okay, that should have been step 1. Remove the denominator, multiply it over. That's step 1, denominator number 1. Number 2 is parenthesis. Break up the parenthesis, and then we get this. And then we have to solve for e to this one. And then I could have done other things, but there's too many zeros, so I simplified. Removed 2 zeros by dividing everything by 100. And then, yeah, flip it over and solve. And then solve 3 over 50, 0.06. That's not the answer. That's exponential, is 0.06. So we have to take the logarithm to find out t. So taking the log of this, we remove the exponential. So we get log of 0.06. Okay, flip over -0.3 as well, finally, and we get this answer. Punch into calculator, you're going to get whatever. By the way, this model is extremely important model. This kind of thing is called a logistic model. E over 1 plus 8 times e to the negative kt form. When t is very, very small, then e to the negative infinity times k, so this is e to the positive infinity, so it's humongous. So entire denominators become really big, so everything goes down to 0. Now when t is really big, positively big this time, then we have e to the negative infinity, so this is 0, so this part drops out, and we have e, equilibrium. For example, this function has this kind of graph. Oh, from -10 to 10, it looks like just plain exponential, just increasing. Okay, -50 to +50, how about that? Okay, now I can see here, to the left-hand side, to the negative infinity, going down to 0. To the right-hand side, to positive infinity, converging to 500, the equilibrium. So this kind of thing is measured, this kind of thing is used typically in population models in a closed environment. So if you grow some bacteria in your lab, in your container, then population model becomes kind of like this. Epidemic model is another example. Disease being spread out in a certain closed environment. At first, really slow, but explode and eventually stabilize. A lot of people are being killed off. In that case, things are a little bit different. But you see, this is a kind of situation that people who would get sick and get immunity will eventually get immune. So it's not that bad a situation. But yeah, if the disease is more serious and a lot of people are dying, then it doesn't work like this. And then rumors spreading out in social media, and so on and so forth. All kind of things are modeled like this, and in this kind of population model, when will the population be 200? That's a kind of question associated to that. Here's another problem that is quite similar, and well, stop the playback and do it on your own. See if you do it right. Did you try? Well, kind of like this. Step 1, denominator, so multiply over. So we have that. Flip it over to the other side. Step 2, parentheses. So break up parentheses by distributing this. Then we have this equation. Okay, all right. Now the like terms. Well, this is exponential term. So 1 is constant term. So flip it over to the other side, and we have 3.5. Okay, divide by 2.5. We get exponential is 1.5. Okay, that's positive. So you can take the log. And then log and exponential cancel each other out. So eventually we get negative 0.4. T is log of 1.4. You can calculate log of 1.4 into calculator, but I'd rather wait. I'll divide by negative 0.4 first and then punch into calculator. I get about negative 0.84. That's the t value. So if t value is time, then about 0.84 time units ago in the past, that this population was about 10.0. Logarithmic equations. You can use some log rules. Do you have enough time? Okay, I'll just show you one problem. Okay, all right. And the key technique is to combine into single logarithm using log rule, log plus log, so I can combine this product, and then 2 to the third power. So this is equal to 8. We have a quadratic equation, and then you can solve it, break up and regroup and refactor and solve it, and then check your answer back into the original equation for possible extraneous solution. Turns out one is okay, the other is no good, so we have only one solution. Make sure you check all those. So you can use some log rules to combine all these logs, many logs, into a single logarithm, and then go from there. These kind of problems are more or less linear. Follow the standard process. Denominator number 1, parentheses number 2, like terms number 3. You see, work those out, and then you may have to use some log rules. What if you have arbitrary basis? Oh, never mind. I don't think anybody will use these kind of things in this course. I guess other than these log rules, exponential equations are more important for this course, especially these kind of models. Logistic model, or maybe a plain exponential growth model. To a certain degree, this thing falls into some application territory too. Okay, so much for section 2.